Hey everybody, today we're going to talk about the differential equation, review a little bit about what we did with springs and pendulums, and then also now talk about drag, which we didn't talk about last fall. So differential equations are equations where the variable and the derivative are in the same equation. So we have springs that we did, we have pendula that we did, and then we're going to talk about drag. So the differential equation always is going to start with F equals ma or torque equals I alpha, always. And then the differential part is going to come from the A or the alpha. So either it's going to be a second derivative of theta or x, or it's going to be a first derivative of speed. And which one you pick depends on what your force or torque variable is, because you need to have those variables match. So for springs, we have F equals negative kx. So if we make F equals ma, our F part is going to be in terms of x. So we want our A part in terms of x. And that's why it's the second derivative of x. Why we don't use dv dt is because this is an x, not a v. For pendula, our torque is equal to negative rf sine theta, which usually the r is going to be the distance to wherever the pendulum center of mass is. And then mg is going to be the force that's causing that, and then the sine of the angle between them, which we then use the small angle approximation to get rid of sine and make it just theta. So torque equals I alpha is going to become that negative xmg sine theta is equal to I. And then because this is theta, we want this to be theta, which is why it's a second derivative in order to have our alpha. So now let's look at drag. So you start by drawing the free body diagram, then you write the force equation, and then you replace with your drag equation. And if you're doing a differential equation, it's always going to be first order, so it's going to be just the, it won't be a v squared, it'll be a vv. So you're going to have our weight going down is the direction that it's going to be accelerating, so we're going to make that positive, is mg. And then opposite that is going to be vv, which is the drag force. So we're going to have mg minus bv is equal to ma. To do a differential equation, you need to replace the acceleration with a derivative. But because in this equation we have a velocity, we want to make sure that we're replacing it with dv dt. We don't want to use a second derivative in this one like we did with springs or pendula, because it's a velocity that we're making our equation for. And that's it. That's our differential equation. People always think this is a lot harder than it is. About every third year or so, the AP folks will have you write a differential equation on a free response question for drag, and this is all you need to do. So you go ahead and you write the free body diagram, write your force equation, replace acceleration with dv dt, and that's it. That's all you need to do to write that equation. So terminal velocity, you should know how to do that, and we did that last fall. So in terminal velocity, the forces are balanced. So the drag force just balances out the weight of the object falling, so that it then falls at constant speed. And that constant speed is the terminal velocity we're looking for. So since it's constant speed, our acceleration is 0. So in our equation, the sum of the forces equals ma, a is going to be 0. So what happens is it starts from rest, and it falls, and as it gets faster and faster, this drag force gets bigger and bigger until it balances out the weight. Okay, so mg minus b times the terminal velocity is equal to 0. vt is equal to mg over b. Again, a lot easier than people think it is. So figure out the terminal velocity. So the bottom line is that often it's not necessary or worth it to solve these things. A reminder that if you can get 70% of the points on your AP exam, you've got a 5. So you don't need to necessarily spend a lot of time solving this differential equation. I will go through how to do that So if you have time and want to do that, you can, but I'm going to show you the things that are going to get you the most points and probably 70% at least of the points on this problem. So first you write the differential equation. So again, free body diagram, force equation, replace A with dv dt. Find the terminal velocity. They'll probably ask you to do that as well. Again, A is 0, solve for vt. The next thing is sketching what a graph of the solution looks like. So you can do this without knowing what the equation looks like. We know it's going to start from rest, so v is going to be 0. We know it's going to speed up, so v is going to get faster, but it's going to speed up at a slower and slower rate. And then eventually it's going to reach terminal velocity, so it's going to flatten out. So we know what that value, that asymptote is, and they will ask for that. And you can figure out what that looks like. So again, you can do this without solving a differential equation. And then often it's good to know the general form of the solution. This tends to show up more in multiple choice questions than it does in free response, although if they ask you to solve it, they'll want you to solve it. And it's going to be a 1 minus e to the negative t type equation. So, looking at this, I think that makes sense, that it's going to be an exponential function. So now let's go through how you solve this thing. If that's something you have time to do and want to do, here's how you do it. So the solution of this is done by a process called separation of variables, which is sadly more complicated than the guess and check that we used for the second order differential equations for pendula and springs. So separations of variables, you have to get the v's and the dv's on one side of the equation and the dt on the other side. And then if you set a equals 0, you can solve for terminal velocity. Okay, so I'm going to take this equation and get it so that I've got all the v's on one side of the equation and no v's on the other side of the equation. So that's the first step. Usually when AP is awarding points for solving this, this is worth a point, getting the variables separated out. So if you can at least get this far, that's one more point. And you might be up to 12 out of 15 at this point if you can do all the other things that I just said you needed to do. Okay, so now you integrate both sides from t equals 0 to time t, and v equals 0 from speed v. So on this side, we're going from 0 to v. On this side, we're going from 0 to t. The right side, really not bad, because this is a constant. So the integral of dt is just t. So that's nice. So that's not bad. The left side is where things get more interesting. So on the left side, we need a u substitution. So let's say u is equal to v minus vt. So then du dv is equal to 1, which means that du is equal to dv. So now we rewrite that integral as the integral of du over u. And if you're thinking, good grief, I don't know how to do that, your AP sheet to the rescue, just like it was for doing derivatives of sines and cosines. On the AP sheet, it tells you that du over u integrated is the natural log of u. That's where the e comes in, okay, plus c. So ln of u plus c is equal to the negative b over m constant t. So now you substitute back, whoops, let me move my face. So you substitute back in, so you substitute your u back in, and because you're doing limits of integration from v to 0, that c you don't need to worry about. So you have the natural log of v minus vt, so v minus the terminal velocity, integrated from v to 0 is equal to negative b over mt. And now we're actually, we're getting there. This is actually not terrible. So we have the natural log of v minus vt minus the natural log of negative vt is equal to negative b over mt. But one of those awesome identities that you learned somewhere along the way is that the natural log of a minus the natural log of b is equal to the natural log of a divided by b. So we do that. Now we combine them. Woohoo! All right, home stretch. We're going to raise both of these, e to the these powers, to get rid of the natural log. So if we raise e to the natural log of this power, then we just get v minus vt over negative vt, and then e to the negative v over mt. And now we solve for v. So we got negative vt over negative vt, that's 1. And then we have v over negative vt, that's minus v over vt. So I just switched the order there. Then we're going to move the 1 to the other side and multiply everything by negative 1. And then multiply through by vt. And there we go. And if we want to substitute in what vt is, we've got that. And here we go. So the general solution of this differential equation has the form of v equals vt times 1 minus e to the minus something t. So now let's look at the graph of the solution. So if we look at the limits t equals 0, so if t equals 0, then that becomes 0. E to the 0 is 1, which means that v is equal to 0. And if t becomes infinity, we have e to the minus infinity. That's 1 over e to the infinity. 1 over infinity is going to approach 0. So that means that we're going to get to vt. So now if we draw and label any asymptotes, that's our graph again that we were talking about. And sometimes it's good to know what the other graphs are going to look like too. So if you think about what the position and acceleration are going to look like, displacement is going to be 0. So it's going to start at 0, and then it's going to get bigger as the speed increases, and then it's going to level off and become linear as we reach terminal velocity. And our acceleration is going to start at gravity, and it's going to get less and less and less until it goes to 0. And so they may ask you to graph a yt and an at as well.